Okay, so our next speaker is Dr. Mark Jensen. Dr. Jensen is the chair in nuclear science and engineering at the Colorado School of Mines in Golden, Colorado. He is an expert on the nuclear fuel cycle and has worked extensively on radiochemistry and advanced energy systems. He's going to present Energy at a Crossroads: What Powered the World in 2024 and What to Expect in 2025 and Beyond. Welcome, Dr. Jensen.
Super. Thank you so much. Well, thank you so much. I don't bite. You should all move closer so you can see the slides. So, all right. Well, super. I'm really excited to be here today. Um, Partly because at the School of Mines, we do a lot of research in the nuclear fuel cycle, the front end of the nuclear fuel cycle, in rare earth chemistry, in radium chemistry, like we were just hearing about. And so it's just a great opportunity for me to see all the stuff that we talk about in class and we study in the lab being implemented here in Blanding. It's just a really great trip for me. So I appreciate the invitation very much. So this is a pretty plugged in and astute crowd. So my first question for you, you might do really well at this. And in fact, there are no right answers, but let's try something to start out here. So when you think of nuclear energy, what do you picture in your mind when you think of nuclear energy? So everybody just take a second, think of a picture in your mind, and let's see if I can guess what they are. So, all right. Okay. How about nuclear accidents at a place like Chernobyl or Fukushima? Maybe. I hope that's not the first thing Curtis thinks of, but all right. Okay. Maybe if you said, maybe you think of this. How about this? Nuclear cooling towers. Yeah, right. So now these aren't actual nuclear reactors. This is part of the overall nuclear power plant. So, but those are the cooling towers for a nuclear reactor. How about this? Nuclear explosions. Well, maybe not. But if I were doing this in a general audience, I'll bet you that some people, this would be really what they were thinking about. A few years ago, there was a great study using social media posts. And one of the things that in the general public, they most often think of when they think of nuclear energy is Homer Simpson. So you might think of Homer Simpson, you might think of glowing rods of radioactive stuff. That's not what a nuclear fuel rod looks like. It is not. Usually they're about 12 feet long and about as big around as my pinky. So, all right. Okay, here's the last one. How about this? How about the sun? Did anybody think of the sun? Yeah, the biggest nuclear reaction, source of nuclear reactions in the whole solar system is our sun. Okay, now it's not the nuclear fission reactions that happen in the uranium, it's nuclear fusion. But all of the sunlight and all of the warmth that we get from the sun is really degraded nuclear energy. It was nuclear energy produced in the sun. It got kind of lowered in energy and came across 93 million miles to planet Earth. And so all of our solar energy, all of our wind energy, which is driven by heat from the sun, right? All of our fossil fuels, which were originally generated from photosynthesis before the plants and animals went down into the ground and got turned into petroleum, is all really nuclear energy originally. So anyway, something to think about. But so everything starts as nuclear energy, practically everything. But so my topic for today is to talk about the sources of energy in the United States, where we get our energy from today, how that flows through our economy, basically, and what this is probably going to look like in the future, and how energy fuels fits into this overall. So every year, the U.S. Department of Energy, through the Energy Information Agency and the Lawrence Livermore National Lab, every year they publish an evaluation of the energy use in the United States. And I had hoped to have the most up-to-date information, which would have been for 2024, but they put it out in October every year. And well, this year the government hasn't been putting things out in October. So I just missed the 2024 cutoff, probably in a week or two. I could show you this figure for 2024, but we're working off of 2023 for this presentation. Okay, clouds stay so we can see the screen, right? Okay, so now this is called a Sankey diagram. And a Sankey diagram shows the flow of materials, or in this case, energy, through a system. On the left-hand side, we have all the different sources of energy that we use. So up on the top in yellow, we have solar energy, and then in red underneath it is nuclear energy. We've got hydro in blue and wind in magenta and geothermal. Then in the light blue, we've got natural gas. The gray is coal. The light green is biomass, and the dark green at the very bottom is petroleum. Okay, and now you can't read I can't read the numbers here. I'm sure you can't read the numbers. Okay, but the lines that come out of each one of those boxes, the thickness of that line represents how much energy is flowing from that source. And so now, from where you're seated right now, if you look at solar at the very top, or wind or hydro, right, they're tiny little lines. As much growth as has happened in wind and solar energy over the last 20 years, they're still these tiny little lines. They only represent a few percent of all the energy that we use. Nuclear is a big fat red line. As we heard earlier today, it's about the third biggest energy source that we have. So, all right, so we have these energy sources on the left-hand side. Now, since they're kind of hard to see in that format, I made a pie chart to make them a little easier to see. So here we have our various sources of energy in the United States. And you can see that petroleum and natural gas make up the biggest part of our energy use. Each of them account for about a third of the energy that's produced in the United States. Nuclear and coal are about the same, and they come in at just about 8% of the primary energy produced, and there's everything else. Now, if you look at this pie chart, right, almost all of the pie chart is made up of things that we have to burn to get energy. In fact, that accounts for 87.3% of all the energy that we use in the United States today. Okay, despite all the work that has gone on to replace cars with electric vehicles and to electrify things, it's still the case that almost 90% of all the stuff, all the energy that we get, comes from burning some sort of fossil fuel. So, now, not all of this goes into making electricity. About a third of it, 34.6% of this energy, eventually gets used to make electricity. And the other 2/3 either gets used directly in industry to heat something up, to heat our homes with natural gas, or maybe if you live in the Northeast, fuel oil or something like that. Or transportation. That's the other big one. Now, if you take, so when I was looking at this chart, I thought, something very interesting about the chart is more than half of this energy at some point either uses uranium or rare earth elements in the generation of this energy. So in fact, almost 55% of the energy uses either rare earths or uranium. So we heard some of these rare earth applications before. In the petroleum industry, to make gasoline, we use rare earths as catalysts to convert crude oil into gasoline. In solar power, now solar panels themselves do not use rare earths, but solar panels only make direct current, DC electricity, and what we get out of the walls is AC electricity. And so to convert that DC electricity into AC electricity, you need an inverter. And an inverter runs on magnets, and those magnets are rare earth magnets. And so we use it for that. Rare earths are used in batteries, and so for solar and wind energy, energy storage in batteries is a huge deal. Of course, we have uranium and nuclear fuel that we all know about, but rare earths are also used in some nuclear fuels as what we call a burnable poison. And that helps us keep the fuel in the reactor longer and be able to run the reactor safely and more stably over that time frame. And then, yeah, so in wind power, we need magnets in wind power. So the wind farm up at Monticello, rare earth magnets in those wind turbines there. So, and even hydroelectric power uses rare earths in generation of electricity. So, the Blanding mill is critically important, in case you didn't notice. All right. Okay, so back to our energy flows. Okay, so we've got this energy. It's starting on the left-hand side of our figure. Most of it is going into combustion and burning things. About a third of it eventually gets made into electricity. And so in the middle of the figure here, and we'll zoom in on this in a second, we show where the different kinds of energy flow. And eventually, we have a set of pink boxes over on the right-hand side that show us where the energy use goes. So about a third of it goes up into the orange box near the top in the middle, which is our electricity generation. And then we go pink. All right, so let's zoom in here. And so where does the energy wind up being used? So about 15% of our energy we use in our homes for residential applications. Some of that's electricity, some of it's natural gas, or that we bring right into the homes and use for cooking and heating. So that's about 15% of the total energy. 12% is used in commercial applications. This is separate from industrial. So commercial applications. Now, the commercial applications category includes data centers. We've heard a lot about data centers in the news over the last year-ish and AI and stuff. That's where this category, that's where data centers fit under commercial here. And so that's about 12% of all of the energy. 35% is used for industrial production, and almost 38% goes to transportation. Okay, now another interesting thing about this diagram is that not all of the energy that we produce actually gets used. In fact, only about a third of the energy that we produce actually gets used. 2/3 of the energy is wasted. It's wasted energy. Most of that is heat that we don't use, right? And so it might be heat in the engine of your car when you burn your gasoline. And if you ever park your car in the garage in the summer and come back an hour or two later, your garage is roasting because of all the leftover heat from the car. And that's why you have a radiator in the front of the car to help remove the heat. Yeah, so we have wasted heat there. In generating electricity, most electricity, as we saw earlier today, is generated by heating up water, turning a steam turbine. That process is not super efficient. Only about a third of the heat that we put into the water gets made into electricity. The other 2/3 is wasted. And so there are efforts going on to take and try and use that waste heat and do something useful with at least some of it. But there's always this wasted heat. Now, an interesting thing about renewable energy, particularly wind and solar, is they don't waste nearly as much energy, right? And so when you generate electricity from a wind, solar, or hydro source, most of that energy actually gets turned into electricity. And so even though when we looked at the Sankey diagrams, the lines connecting them to other things were really quite small. All of that line is getting made into something useful, almost all of that line. Whereas if we look at the natural gas or coal, petroleum, nuclear, much of that initial energy that we start out with is not being used right now. And this is something that we could do much more efficiently. All right. Okay, so if I'm going to project into the future, it might be good to see how energy sources have changed in the United States with time. And so, sort of the very last half of the graph here is probably the most relevant. So we sort of had an age in the 50s where petroleum kind of became our biggest source of energy, displacing coal. Coal was kind of level for a while, but in, say, the 70s and 80s, it grew as being useful. Also in the 50s, use of natural gas really exploded. And so if you were going to look at, say, the 1990s, the big three sources of energy were petroleum first, and then natural gas and coal were about the same. But over the last 20 years, coal has fallen out of favor overall. And so you can see the black line there, coal dropping off. And almost all of the energy that we get from coal has been replaced by an increase in natural gas. That's mostly what's happening there right now. In 2024, the amount of primary energy that we get from all renewables, nuclear energy, and coal, those three together are all about the same. And if we add them up, they represent about a quarter of all the energy that we use, the rest being natural gas and petroleum. All right, so what might this look like, say, 25 years from now in 2050? Well, the Energy Information Agency is also projecting ahead, not just reporting on what we have today. And so their projections for 2050 are that as a country, we will use about 5% total less energy that we use today. So energy use overall for everything, not going up, going down a little bit is their projection for 25 years from now. Natural gas use and petroleum use, they're projecting to be about the same. Same for nuclear. I don't necessarily agree with that, but that's what they're projecting. And then their projections are that coal will be zero, and that we'll use almost no coal. There are a few applications where we might still use it, like actually as part of alloying steel, making steel, but their projection is for energy pretty much nothing. And then renewables will grow in their projection to be about double what we have today. So those are the projections for 2050. All right. Now, they also project that by 2050, the US will use somewhere between 25 and 80% more electricity. So our overall energy usage is supposed to go down, but our electricity usage is supposed to go up, potentially by a lot. And earlier this morning, we heard from Duke Energy that they're looking at 2 to 3% annual increases in energy. And well, if you look over 25 years, that just about matches what the Energy Information Agency is saying is going to happen across the whole United States. So, what's that going to look like for uses of energy? So, they're projecting that our residential energy use will stay about the same. Commercial energy use will increase from about 12% to 15%. So that's like a 25% overall increase in commercial use of energy. And guess what? Data centers are in the commercial part, and so this is the big projection for the increase in energy in the commercial use. Industrial energy use is projected to increase, and transportation energy use is projected to decrease substantially. Why would this be? Well, this would be from electrification of our vehicle fleets. Electric cars are more efficient in how they use the energy compared to combustion engines. And if you also kind of put together the likelihood that electric vehicles will be powered through this increase in renewable energy, you also get an increase in efficiency from the primary energy where you're not wasting all that heat. Okay, so what areas should we be looking out for in the future? So I said I disagreed with their projection for nuclear energy. In last year at the International Climate Conference, COP28, the United States joined a number of other countries pledging to triple the amount of nuclear energy that we would use. I don't know if we will be able to do that in 25 years because right now, as we heard this morning, we have 94 big nuclear reactors in the United States. And so if we were going to triple nuclear energy, that would be, we need to build hundreds of nuclear reactors in the next 25 years. That would be great. I hope we do. It's a big lift. I don't know that we will. But another way we could look at this is that right now, all we have are nuclear fission reactors. Some companies are getting pretty close to potentially producing electricity using the other nuclear reaction, nuclear fusion. And so we'll see. Some companies are saying in the next 5 years, we could have nuclear electricity from nuclear fusion instead of nuclear fission. If you look at historically how long it took us to go from our very first nuclear chain reaction in the Manhattan Project to making electricity, it took about a decade. And the very first part of that, we were busy fighting a world war. So, but 10 years to go from sort of the first demonstration to making electricity has historical precedence. It was a few years ago that Lawrence Livermore National Lab demonstrated a fusion reaction. And so 5 years, 10 years from now, could we have electricity from fusion? It wouldn't be out of the question. So data centers and AI. This is likely to be a very important part of our energy use in 2050. 2024, Lawrence Berkeley National Lab said that in 2023, 4.4% of all our electricity went to data centers in the United States. 5 years later, which is only 3 years from now, 2028, they're projecting that between 6.7 and 12% of all our electricity will be for data centers. And then project out another 22 years to 2050. And there you have your increase in electricity usage in the commercial part of this. A few years ago, people would have been talking about cryptocurrency as being the big source of this energy use. It's not. It's a small part of this increase. It's really AI and big data. So other area to watch for energy use is electrification of transportation. In 2024, we used only 0.06 quads of energy. The whole United States used 94 quads. It's an unusual unit, but okay. So basically less than 0.1% of all of our energy use went into electric vehicles in 2024. By 2050, they're projecting 45-fold growth in this. And so at that point, a few percent of all our electricity use, of all our energy use, and a substantial fraction of our electricity use could be for transportation. Now that 2.7 quads is equivalent to all the electricity that is generated by nuclear energy in the United States today, which is about 20% of all the electricity that we use. So that could be a big deal. Another thing that you might not think about much is that worldwide, one of the biggest projected uses of growths in use of energy is for cooling cooling buildings, especially in places that are second and third world countries today, places like India, the Middle East, where we're seeing economic growth. And one of the first things that people want to do as their economic conditions improve is put an air conditioner in their house. And so projections for that right now, today, cooling only uses about 1% of the world energy, but that's projected to triple by 2050, and worldwide that would be about 20 quads of energy or 1,000 nuclear reactors. So there's a lot of growth, full size nuclear reactors. All right. And then another thing that we might not think of much, but was mentioned earlier today, is water use. Water use. And so by 2050, they're projecting that water use worldwide is going to increase by 20 to 50% over today. And that to get that water, we're going to need energy, whether it's to desalinate water from seawater, do that, or to access and improve not salt water. They're projecting a big increase in energy for that. And so we're looking at 4 quads of energy in 2030. And by 2050, they're talking worldwide about that doubling or tripling. And so again, this would be the equivalent of hundreds of nuclear reactors worth of energy use. So there's my summary of where we're with energy today and what we're looking at potentially for energy use in the future. So thank you. Yes. Yeah. So today, nuclear represents just under 20% of the electricity that is actually made and used. Together, wind, solar, and hydro together are also just a smidge over 20%. So if you put all the traditional renewables together, they are roughly equal to nuclear energy today. The actual breakdowns, if I look at these numbers on our chart here. So one thing I didn't say, this chart in solar does not include residential solar. And so if we included residential solar in this, it would basically double the amount of solar energy. And so doing the math as quickly as I can in my head, it looks like solar with residential solar is about a third of the energy produced, electricity that's produced by nuclear energy, and wind is just about equal to that. What are the costs? Well, yeah, this is going to depend on where you live. It's going to depend on, I mean, it depends. It depends. Yeah. So I'm not prepared to accurately answer that question.
Oh, we have one more question here.
You would say you disagree with the EIA projection on nuclear. Can you just give us a ballpark of where you think you'll be at in the energy mix
For 2050, right? So like we heard, utilities right now are pretty strongly pursuing license extensions, right? And so 20 years from now, I think that most of the 94 megawatt or gigawatt scale nuclear reactors will still be running, right? And so that's going to keep, right, like just that, no change there. That's going to keep us at about 8 quads of energy from nuclear, or energy being made by nuclear and then being made into electricity. So anything on top of that, so small modular, penetration of small modular reactors, this idea that that just came out this week, 10 more full-size nuclear reactors in the next 10 years. So that's a 10% increase there. So so if we include that, there's that part. And that's the fission side of things. If we do 25 years from now have functioning fusion reactors, not that there aren't problems with this, there are problems, but so could we have twice as much nuclear energy, fission, large fission reactors, small modular reactors, and fusion reactors? Not out of the question.
What about thorium?
Thorium, yeah. So thorium is awesome. Thorium is awesome. So about 10 years ago, I was at a DOE workshop, and as part of this workshop, they wanted us, they posed a question. They said, if you could start with a clean sheet of paper and design the optimum nuclear energy system, what would you do? And so I walked into that meeting and I said, thorium fuel cycle. That is what I would do, because when you go in a thorium fuel cycle, the intermediate nuclear waste problem goes away. And so from a few hundred years to 50,000-ish years, the radioactive waste, a high-level radioactive waste from a thorium-fueled reactor is much less radioactive than from a uranium-fueled reactor. And that's because there's almost no plutonium in a pure thorium fuel cycle. And so those things go away. They're not really important. And so this was a workshop, exercise. And so everybody puts their ideas in. And one of the leading nuclear engineers from another university saw my idea and he goes, this is a terrible idea, and throws it out. And his point was that it takes decades to qualify material to be used as a nuclear fuel in a reactor. And so it would take decades to get a thorium fuel ready to go in a nuclear reactor. Now, should we throw it out for that reason? Probably not. Was he adhering to the spirit of the workshop that said, start and think of what might be best if we were going to start from ground zero? No, he was not. But so it has some advantages for sure. I would rather chemically process uranium than thorium. If I had to do the chemistry, I would rather do uranium. I think that is easier. But
Okay, well, thank you so much, Dr. Jensen. Thank you for those great perspectives and for offering that here to our audience.